Good morning. I hope you all are doing well, and I appreciate having you here on this blustery Monday. Here's kind of an overview, first of all, of what's happening this week. First of all, I really appreciate your exams, and I will return them this afternoon. Some people did really well, so I'm really pleased. But anyway, this afternoon you'll get it back in an email. And when you get your exam back, first of all, you'll see your total grade at the very next to last page, which was the last page when you did the exam, but it'll be the next to last page now. And the very last page of the exam will actually be a summary sheet, which is kind of like how you're doing in the class today if I had to give you a grade. And I do encourage you to check it out to see, make sure that the scores that I have listed are the scores you actually got back, because I do make mistakes, I'll confess, and so call me on it if there's a mistake. But also, if it says you're like missing a lab or something, it's really important to get those labs in because it's part of the lab completion bonus at the end, stuff like that. So that'll happen this afternoon. And then this Wednesday, when you come, bring problem set number 4, which is mostly over balancing equations, power of equations, stuff like that. Bring the completed percent KClO3 lab that we did last Wednesday, and bring a printed copy of the net ionics lab. Net-ionic reactions will be the focus of this lab this week, and it's really important that you have a printed copy you can write down. And then Wednesday night, I'll release quiz number 4, which has got stuff over balancing reactions, and that'll be due Friday, 9 a.m. as always. And then just one final announcement is that next week, Friday at 9 o'clock, which is November the 5th, the rough draft of the class presentation paper is due. And all of you have a class presentation element at this point reserved, and you can start researching it. The rough draft to me means at least 2 type pages. Now, if you turn in more, awesome, all right, but at least 2 type pages. And I also want to see 1 peer-reviewed research abstract. And those are something you can look up very easily on the Mount Hood website. If you go to the class presentations, frequently asked questions, the FAQ, there's a website in there that you can click on, and it sends you to a Mount Hood database, and you literally just put in rhodium or magnesium or whatever your element is, and I promise there'll be a gazillion different articles that pop up, and I want to see one of the abstracts from one of these papers, all right? And the abstract with a citation just lets you know that your element is still relevant, all right? There's still research being done and stuff like that. If you have questions on any of this, absolutely you can email me. I'll start sending out more messages as we get closer to next week, Friday. Just wanted to give you a heads up. Any questions on that stuff? Sweet. So we left off last Monday, and we just barely began the idea of what exactly a solution is, all right? And a solution, as we talked about, has 2 components, the solvent and the solute. And the solvent's boring definition is it's the component where the physical state is preserved. So let's say we were making a sugar solution, all right? The sugar would be a solid and the water would be a liquid. As we mix the 2 together, it looks like a liquid, all right? So the liquid with the water is the solvent, all right? It's usually the bulk component. But the interesting part is the solute, and the official definition, it's just the other solution component. But we said, for example, earlier when I said sugar solution, I didn't say water solution because water is kind of boring. So the interesting part is the solute. So hydrochloric acid is usually a solution. Hydrogen monochloride, or HCl, is the solute. Water would be the solvent, stuff like that. And we also talked about the terms soluble and insoluble. All right, soluble just means that things dissolve well. So sugar in water dissolves. You have just one phase. You have just a liquid. That would be soluble. On the other hand, if you go to the river and you throw rocks in the river, they don't usually dissolve in the water of the river. So we would say that rocks are insoluble. They stay as solids when they're in the water. Any questions on that stuff? They all begin with SOL, and SOL has other meanings, and this is a G-rated class more often than not. So just remember they're all a little different. So solute plus solvent equals solution. But first, a celebration, although 2 days late. Think? Yes? Yes? There we go. Little music here, kind of wake you up and stuff this morning. Mole Day was Saturday, and this was the closest lecture I had to it. 10 to the 23rd, October 23rd. Oh, it's Saturday.
Happy Mole Day to you. Happy Mole Day, dear students.
All right, so anyway, chemists get really excited by Mole Day. Now, officially, it's 6:02 a.m. or p.m.
Are you?
And you can see that this is a syllable.
6:02 times 10 to the 23rd. Happy Mole Day to you. How many moles are
All right, this video goes on for a while, and it's obviously too early to truly appreciate the humor of Mole Day, but I did want to say that I'm sure you were all celebrating in earnest Saturday morning, 6:02, or Saturday night, 6:02 p.m. For Mole Day. Chemists get kind of excited by this, you can probably tell, so anyway. All right, no questions, good. So we talked a little bit about this last week, Monday, and this is the solubility guide for Chem 221, actually all the way to Chem 223. And this is just a rough kind of little thing that says if something is soluble, which means it dissolves in water, or if it's insoluble when it doesn't dissolve in water. And when we talked about this last week, the things in the upper left corner, these are always soluble. And if something is soluble, that means we're going to write AQ next to it. AQ stands for aqueous. And aqueous in this context means that this substance dissolves in water. So everything in the upper left here is soluble, and would write AQ. But there are some important exceptions. And if you run into one of these, then you would say it was insoluble. And insoluble means you'd write a little S solid next to it, and that shows that it doesn't dissolve. Now in this lower part down here, the left-hand side, these are the insoluble ones. So for these, you would write an S next to it. They don't dissolve, but there are some exceptions to it. And the exceptions here would mean you'd write AQ. So let's say that you had a barium nitrate compound, and you wanted to know if it dissolves in water. Well, the anion, or sometimes the cation, will be the key. And if you look at this list long enough, nitrate is right there. And nitrate, and as well as chlorate, acetate, sodium, potassium, ammonium, no exceptions. Like there's no exceptions right there. So that means that anything with nitrate is going to be, for us anyway, soluble, AQ. So you're working in graduate school and you're working on blah, 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 nitrate, and I have no idea what blah, blah, blah is. That's okay, because the nitrate will be enough to tell me as the chemist that it's soluble. It should dissolve in water. Now, barium chloride, all right, chloride, bromide, and iodide have very similar reactivity. And these three are soluble unless they're with silver, mercury, or lead. Barium is not silver, mercury, or lead, so that means, like most chlorides, it would be AQ soluble, all right? On the other hand, barium sulfate, all right, sulfate is right here, and most of the time sulfate is soluble, AQ as well. But one of the exceptions of sulfate, as you can see right there, is barium. So barium is one of the exceptions. That means we would write this as BaSO4 solid. Barium sulfate does not dissolve. Now, if you took solid barium nitrate and placed it in water, it would dissolve, all right? You wouldn't see any solid. Maybe a color change or something like that. In this case, there wouldn't be. But anyway, it would look like it was just water, all right? And the same thing with barium chloride. If you took solid barium chloride and you placed it in water, it would dissolve. That's what AQ means, and you wouldn't see any solid. However, if you took solid barium sulfate and you put it in water, it's not going to dissolve. You would see a physical solid. It's a white solid. You don't need to know that, but that's what it is. Barium sulfate, you would actually see the solid chunks kind of running around. So insoluble means you're going to see a solid. These ones up here, not going to see anything. They'll dissolve really well. This guide is really helpful. We use it all the way through Chem 223. There's more to solubility than we're talking about here, but this is a pretty good overview. And if someone in the hallway says, "Hey, Russell, does magnesium fluoride dissolve in water?" Well, I have never dealt with magnesium fluoride per se, but I do know that magnesium is an exception to fluoride, so that means that it would be insoluble. It shouldn't dissolve. So it's kind of like a rough guide that's helpful to the chemist, like on the spot kind of stuff. Questions on that? All right, we'll do more of this on Wednesday in lab. The lab is going to really focus on how these kind of things work out. Now, in the regular class, this would be something that I wouldn't say memorize, but I would say become very familiar with. And I'd want people to know this and stuff for quizzes and exams. And this year, everything, for better or worse, is a little strange. So this slide was just my attempt to tell my students some things that are basically always soluble, all right? And sodium, potassium, lithium, ammonium nitrate, chloride, perchlorate, and acetate, these ones are always soluble, always AQ. So you're making in lab blah, 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 perchlorate, and again, I don't know what the first part is. Perchlorate will be enough that you can have confidence in saying it's going to dissolve. It'll be AQ. Most sulfates, chloride, bromides, and iodides will dissolve. We're going to run into the chloride, bromide, and iodide exceptions quite a bit eventually, but not right now. So we will run into these, but this is one way to kind of help prepare and stuff if you have. But again, for you in this class, you will always have access to this table. You can look at it and see what's happening. All right, so just as a way to kind of check yourself, which one of these would be insoluble? And remember, insoluble means to write a little S next to it. Well, anything with nitrate, ammonium, sodium, potassium, lithium, automatically going to be AQ. So notice I was able to knock off this one because both ammonium and nitrate are on this list. Anything with sodium, potassium, or lithium, it's an alkali metal, but anyway, those are always going to be AQ. And most of the time, chloride, bromide, and iodide are aqueous, except when they're with silver, mercury, or lead. And you can see that lead right there is one of the exceptions with iodide. It does make an insoluble compound, so that's how we would tell that C is insoluble. And again, what that means, you put PbI2, which is a solid, you put it in water, you will see a solid form. It won't dissolve well, okay? It's kind of a yellow color. On the other hand, if you take sodium hydroxide and you place it in water, it will dissolve. You won't see any of the solid right there. Any questions on that? Okay.
Potassium permanganate is an ionic compound. It dissolves readily when mixed with water. Dissolution involves the breaking of the bonds that hold the compound together. The ions become distributed throughout the water, forming a solution. Water molecules are made of hydrogen and oxygen. The hydrogen side of the molecule has a positive charge. The oxygen side is negative. When water molecules contact an ionic compound, such as potassium permanganate, their positive sides are attracted to the negative ions of the compound, and the negative sides of the H2O are attracted to the positive ions of the compound. These attractions allow the crystal lattice to break down, and the compound dissolves.
Sweet. So, first of all, this is what happens when you take one of these compounds and you dissolve it in water. They came in a form kind of like purple crystals, and of course water is water, and you put them together and the solid goes away. It becomes kind of a cool purple solution. This is one of my favorite colors and thing of all time, but anyway, you don't see like chunks of solid running around. Now, why you don't see chunks is shown in this video. So what we have over here, the blue with red dots, this produces a permanganate ion, MnO4 minus 1. The manganese is blue, the oxygens are red, and the whole thing has a -1 charge. And then right next to it, we have potassium ions. Now, normally, these ionic bonds, very strong. Positives and negatives have huge melting points and stuff like that. But little water is amazingly tenacious. And we're going to see that water has a slightly negative side where the oxygen is like pointing to, and it has a slightly positive side in the crux of the V. It looks kind of like a V, and so in the middle part of it, there's like a slight positive part. And in this video, what's happening is when you have a negative permanganate, the positive side of water like surrounds it, and it's able to extract permanganate from this ionic solid. And on the other hand, when you get a positive potassium, then the negative side of water, like towards the red part, they get all around it and they pull it away. Water is able to like get in between the ions, and it separates the positive cation from the negative anion. And it's amazing that water can do this. Water is one of the few solvents that we're going to see that's able to make this happen. So this part down here represents the solid KMNO4, all right? And normally this stuff is super hard to melt and stuff like that. But good old water is able to weasel its way in between the ions and extract them from each other. So you end up with MnO4 minus ions running around and K plus ions running around. Water is able to like infiltrate them. So aqueous solutions are pretty cool, right? Because it's the water's ability to extract this little pieces, cations and anions, from the base. So you end up with no solid. This is like the solid, those positive negatives. It's all due to water. Water is about as close to the chemical idea of the perfect solvent because it's able to do stuff like this, which is no small feat. Anyway, questions? So when it comes to making a solution, all right, it's really water's influence which makes it happen. And that's critical for us in our life systems. All right, blood is basically a bunch of ions running around. I mean, there's more than that. But anyway, it's all water's ability to pull off the cations from the anions, like get them separated out. And there's a lot of really interesting chemistry that happens along the way. Okay. So the question is, how do we really know that ions are present in these aqueous solutions? And that's a great question. And the answer for why this happens is because ionic compounds make electrolytes. Now, if you like drink Gatorade, and you don't have to admit to me you do or don't, but anyway, a lot of times they'll say, oh, electrolytes, man, make you powerful and blah, blah. Well, that being said, besides the advertising components of this, electrolytes in a chemical way are just ionic ions that have been dissolved in like water, so they separate out. And all of the ionic compounds that dissolve in water make electrolytes. If you have electrolytes and you put electricity through the water, it'll conduct. Now here's electricity in a nutshell. Electricity goes from the positive side to the negative side, and it makes kind of like a racing track, all right? And the electrons need to flow like in a circle to make it happen. And the only way they can get from this electrode to that electrode is because the ions allow the electricity to flow, all right? And when you have an ionic compound dissolve in water, this happens really readily, and the electrons will flow. So we call these things strong electrolytes when they dissolve 100%. And so if you have 1 mole of KMNO4, they break up 100% into K plus and MnO4 minus. If you have 1 mole of NaCl, that breaks up 100% into 1 mole of Na plus and 1 mole of Cl minus. So the strong electrolytes would create a very strong light bulb signal, if you will, and that's how we know then that these solutions are capable of having this happen. So we're going to start talking about electrolytes, which are nothing more than positives, negatives dissolved in water. And a strong electrolyte means that 100% of what we put in breaks up into positive and negative ions. Questions on that? Water by itself would not conduct electricity. If you had water that was 100% pure and you did this, there would be no light right there. Without the ions, the cations and the anions dissolved in water, you wouldn't have any electricity go through. So when you hear about people like slipping in the bathtub and their hairdryer falls in and they get electrocuted, all right, it's not the water's fault. It's the ions, like our bodies have sweat and stuff like that, or maybe there was types of soap with ions, whatever. It's not the water's fault per se. It's the ions in the water that allowed electricity to be conducted, which allows the poor people to get electrocuted. So be careful if you take a bath, blah, blah, blah. All right.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
So again, just to reiterate that, a strong electrolyte is just an ionic compound that dissolves 100% in water, all right? And these are just some of the examples, and we'll talk about them. HCl, hydrochloric acid, strong electrolyte. Sodium chloride, strong electrolyte. You must have an ionic compound to make an electrolyte. So notice that all of these have a positive and a negative center. And again, you set it up in the electricity thing, you would see the light go through. The light's able to be conducted. But not all ionic compounds break up 100%. Like maybe in 100 of them, like one of them would break up into positives, negatives, and the other 99 would stay as they are. And we call those weak.
A weak electrolyte is a compound that only partially ionizes in solution. Some hydrogen ions dissociate from acetic acid molecules, but others may rebond at the same time.
Acetic acid is one of the funny acids. It's got an acetate, a CH3CO2 minus, and the H plus is the acidic part. Now normally I prefer to see the acid part listed first and the acetate listed last, so that shows it's an acid. But a lot of times you won't see acetic acid listed that way because of about 10,000 acetic acid molecules, only one of them will break up into an H plus and an acetate ion. Most of the acetic acid stays as acetic acid. This is the acetic acid molecule. It's a very, very small percentage that actually break up into the H plus and the acetate ion. So if you have a weak electrolyte, all right, and you place electricity through it, it's a very dull bulb glow. I mean, it does glow a little bit, but while the strong electrolyte would be like blinding light, weak electrolytes would be kind of like a weak light bulb, if you will, not very bright. So strong electrolytes, all of them break up into positive, negatives, all right, electrolytes. Weak electrolytes, maybe one of 1,000, one of 10,000, something like that, will break up into positives and negatives. And then there are non-electrolytes. And non-electrolytes don't break up at all. And most of the time, the non-electrolytes are compounds which are covalent. They have nonmetals with nonmetals, things that do dissolve in water but don't break up. This is going to be an example, with ethanol, which is drinking alcohol. All right, just so you know, kids, but anyway, this is ethanol. This also applies to things like sugar as well.
Some compounds that dissolve in water, such as ethanol, do not dissociate into ions at all. Such compounds are called non-electrolytes.
Cool. So strong and weak electrolytes, you have positive, negatives, cations, anions that break up, at least somewhat. Non-electrolytes are compounds that don't have positives and negatives. They're all covalently bonded, the other kind of bonding. And there are a lot of compounds that dissolve in water, but they don't break up into positives, negatives. So when you put electricity through these guys, like nothing goes through. Ethanol doesn't have positives and negatives to make the electricity go from one side to the other. So you can imagine electrons kind of stop at one electrode and they can't get over to the other side. There's no ionic charges for them to like dance across to get to the other side. Okay, so backing up just for a second then, we're talking here about solutions, all right? And solutions are really important, all right? The coffee we drink, actually all the drinks and stuff that aren't water are some kind of solution, all right? And when it comes to solution, we think about these electrolytes, which is just positives and negatives. Strong electrolytes break up 100%. NaCl go to Na plus, Cl minus. Weak electrolytes, one of just 1,000 or so, break up into positives, negatives, so they don't conduct electricity as well. And then these guys, non-electrolytes, these are for covalent compounds with organic pieces, carbon, hydrogen, oxygen only, and they don't conduct electricity at all. Okay. So acids, we talked about their naming a little bit in the earlier chapter. We're going to keep coming back to acids and bases here in a little bit. And acids are just, again, compounds that somehow give up an H plus in water, all right? And again, I prefer, and most of the time, the acidic hydrogens are listed first. And we talked about how HCl is hydrochloric acid. Well, there are strong acids and there are weak acids. And all of the strong acids are strong electrolytes. So these are examples of strong acids: hydrochloric acid, nitric acid, perchloric acid, and sulfuric acid. And if you know you have a strong acid, you therefore have a strong electrolyte.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
So if you put 1 mole of HCl in water, you end up with 1 mole of H plus and 1 mole of Cl minus. All of the HCl dissociates into the ions, so this would be a strong electrolyte. And all the strong acids are strong electrolytes. They make the light bulb come on super bright. But not all acids are strong acids.
A water molecule consists of 2 atoms of hydrogen and 1 of oxygen. Water molecules are attracted to a hydrogen ion or proton to form a conglomeration. There are often 6 and sometimes more water molecules around an ion. Because the hydrogen ion is so small, it is thought to have an average of 4 water molecules associated with it at any time.
Sometimes you'll see acids referred to as hydronium, which is a water molecule with an H plus. And waters surround the H plus. So we talked about how in a V, the V is pointing towards the negative side of water. And the negative side of water is attracted to positive ions, even the H plus in HCl or something like that. And so what happens is acids, the H plus is surrounded by these water molecules. And some people think it's 4 water molecules per H plus, some people think it's 6, it doesn't matter. But they represent all of those combinations as hydronium. So it's like the water molecule has an H plus on it to like deliver. And so hydronium is just like activated acid, all right? It's like HCl, it technically isn't really an acid until the H plus breaks away, and you can think about it then as H3O plus, like ready to deliver, all right? So if you hear hydronium, it's just another way of expressing acid, acid being the H plus surrounded by water.
Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
There's a few strong acids, but there are thousands upon thousands of weak acids. And these weak acids, like acetic acid or hydrofluoric acid, what that means is that maybe of every 1,000 or 10,000 molecules, 1 of them will break up. So for HF, that 1 in 10,000 or so would break up into H plus and F minus. But most of the H plus would stay as HF. It wouldn't break up. It wouldn't dissociate into H plus and F minus. So weak acids just don't give off the same number of electrolytes. They're weak electrolytes. And so if you put the light bulb test in a solution of acetic acid, it wouldn't glow very brightly, all right? Acetic acid, by the way, is the active ingredient in vinegar. So if you're a vinegar fan, the zip of it is from the acetic acid. Most vinegars have other kind of spices and stuff in it, so it's not just acetic acid, but kind of a cool thing. So when it comes to acids, strong electrolytes mean strong acids, weak electrolytes means weak acids. There's only a couple of strong acids, but there are thousands of weak acids, and we'll come back to this topic later. Now, bases are kind of the opposite of acids, all right? And a base is just something that gives off hydroxide in water. So hydroxide is OH minus, it's a polyatomic amount. And most of the time, bases are metal hydroxides. So it's a metal with some kind of OH minus. And the most common example by far is sodium hydroxide. Sodium hydroxide has a sodium ion, so that means it dissociates really well. It breaks up into Na plus and OH minus. And the OH minus is what makes a base, all right? It's the source of energy, if you will, for the space system.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
So you can see that all the NaOH dissociated into Na plus, which honestly is kind of boring for us, but it does have the OH minus, the base. And just like acids would absolutely hurt you if you put your hand in them, if they're strong enough, bases, same way. All right, you put your hand in a base and ow, it feels weird. Bases are usually a little bit slippery when you feel them, but if you feel that slipperiness, like get your hand away, man, because that means the base is kicking it. So all the strong bases are strong electrolytes, which means they break up 100%.
On the left is H2O, water. On the right is NH3, ammonia. The dots and lines represent electrons. Ammonia acts as a base in water. It removes a hydrogen ion from water to create hydroxide and ammonium ions. In solutions, only a few hydroxide ions are created at any one time, so ammonia is a weak base.
So just like there are strong acids and weak acids, strong acids break up 100%, weak acids much less though. There are also strong bases and weak bases. And the most important weak base is ammonia, NH3. And so we've run into this already a little bit. Ammonia, NH3, ammonium, NH4 plus. And when ammonia is added to water, some of it, like 1 in 10,000, they dissociate. And what happens is ammonia takes one of the H's from water to make ammonium. But in the process, you end up making hydroxide. And anytime you have a substance which creates hydroxide, you're going to have a base. Now, this is a much weaker base, all right? Like you wouldn't want to put your hand in sodium hydroxide, a strong base. Ow, all right? However, ammonia in water, or ammonium hydroxide, which is what is often labeled as, if you had to, you could put it in there. Now, don't do it, because it can also hurt, definitely, and it depends on the strength, but ammonium hydroxide is weaker, so you wouldn't hopefully feel the same sting. So anyway, weak bases just don't break up 100%, they don't dissociate. Strong bases do dissociate 100%, and they're strong. Okay. So here's a table, strong acids and strong bases. And I want to focus on this here a little bit. There's only a few strong acids and strong bases, all right? There's more than this list, but there's not that many more, all right? But there are literally thousands upon thousands of weak acids and weak bases. So as you start going through chemistry, I highly recommend that you know the strong acids and strong bases. Now in Chem 223, these first 5 strong acids super important, all right? We're going to talk about them a lot. And these 3 strong bases will also be important as we go through. Sulfuric acid has something else going on. We'll talk about that in Chem 223. But if you know the 5 strong acids, the first 5 listed there, and the 3 strong bases, then all the other acids and bases essentially we can consider weak, and they won't be as effective, if you will, in delivering acetic acid or base. Aspirin is actually an acid, all right? Citric acid in oranges and stuff like that is a acid. Ammonia, and there's other ones and stuff out there. So again, what I recommend here is that you kind of focus on the few strong acids and the 3 strong bases, and then by default, all the other acids and bases, if you have to guess, would be weak, all right? And for us here, perchloric acid up to hydrochloric acid, those are the 5 important acids. Don't worry about sulfuric acid yet. Any questions on that? Okay, so it says here, which of the compound is not an acid in aqueous solution? Okay, so here's 5 compounds. To be an acid, you have to have hydrogen, okay? And in a normal acid, if the hydrogen is listed first, that means it's going to be an acid. So if we're looking for the one which isn't an acid, you can cross off B, D, and E. All right, phosphoric acid is an acid, hydrochloric acid, and this is hypoiodous acid. All right, so you knock off B, D, and E because those are definitely hydrogen first. Those are going to be acids. But the ones we don't know for sure then are A and C. They both have hydrogen, so they could be acids, but neither of them lists the hydrogen first. Well, like we talked about earlier, this is acetic acid, and for better or worse, a lot of times the acetate is listed first and the hydrogen at the end. So this one is an acid. NH3, though, is a base. This is one of the ones that reacts with water. It pulls the hydrogen off water to make ammonium, and hydroxide is made in the place. So of these 5, ammonia is a base, all right? It doesn't look like a normal base. It's not a metal hydroxide, but that ammonia, that nitrogen on the ammonia, is actually a little bit basic. And I don't like the way that this is formed, but it's very common. And so I have to bow to this one a little bit. Sorry. Any questions?
We put magnesium metal into aqueous hydrochloric acid. The 2 react. Aqueous magnesium chloride is formed along with gaseous hydrogen.
This is a really fun reaction. Fun being a relative word, I suppose. But anyway, in this reaction, you're taking solid magnesium metal, chunks of metal, all right? And you're placing it in hydrochloric acid, HCl. And the products of this reaction, you can see it bubbling right there. That bubbling is hydrogen gas, all right? And you also end up with some magnesium chloride. And now that we know a little bit more, first of all, we need to balance it. So there's 2 chlorides, it's okay, 2 chlorides, 2 Cls there, and there's only 1 in HCl, so we need a big 2 in front of that. And that's good because hydrogen, one of the diatomics, have no fear of ice clear brew. The have is hydrogen, so when it's by itself, we have to list it as H2. So this is a balanced reaction. The other thing we can do now is start adding the states of matter. So magnesium was chunky, all right? You kind of plop it in. That means it's a solid. HCl is dissolved in water, so it's HCl aqueous. And the bubbling hydrogen means that hydrogen gas came off, so it's a gas. And this guy over here, we don't see anything, so we know it's going to be aqueous. So a solid and a solution made a gas and a solution. Any questions on anything I just said right there? Okay. A net ionic equation is a way we can analyze something like this to see what the action of the reaction is. And we're going to see that in a chemical equation like this, some of the species are more active than others. So in a net ionic equation, we really want to get into the nuts and bolts of this and see what's really happening, all right? And so here's how we can figure this out. Now, after we talked about all these things, hydrochloric acid is a strong electrolyte. It's a strong acid and a strong electrolyte. And just take my word for it, magnesium chloride is a strong electrolyte as well. So really, if you have a strong electrolyte like HCl, we should break it up into H plus and Cl minus, because strong electrolytes dissociate 100% into the cations and anions. So 2HCl would become 2H plus and 2Cl minus. And we're going to do the same thing for the magnesium chloride too, because it's also a strong electrolyte. So we will break that into magnesium 2 plus and 2 Cl minuses, all right? That's what it means to be a strong electrolyte. You break these strong electrolytes up into cations and anions. I would call this step the total ionic, or the ionic part, all right? Like you're seeing like what's around. The punchline for doing this is that you never ever break up solids, gases, or liquids. Now, liquid we have to be careful with here. Liquid would be a pure liquid like water. These are solutions, all right? And solutions you do want to break up into cations and anions. But when you're doing this step, don't break up the solids, the gases, or the liquids. Cool. So you're looking at this and you're like, oh boy, that's exciting, Russell. Well, here's the thing. In chemistry, just like with math, you can separate, you can cancel things that are present on both sides. And on the reactant side here, we have 2 chlorides. And on the product side, to the right of the arrow, we also have 2 chlorides. So what that means is the chlorides, they were there before and they're there afterwards. So they're kind of sitting around watching all of this happen. They are not participating in the chemistry of the reaction. So here's this same reaction, but I highlighted the yellow chlorides there because I really wanted to point out that they're present on both sides of the reaction. And these kind of ions that are present on both reactant and product side have a special name. We call them spectator ions. And the spectator ions are just sitting around watching the world go by. Something kind of zen about that, but in terms of chemistry, they're not participating in the chemistry, all right? It's the magnesium and the H plus that are doing something, but the chlorides were there at the beginning and they're there at the end. So spectator ions are kind of just sitting around. They're not doing anything. And as we'll see in a little bit, we could have substituted them for something else. And I'll talk about why that's important here. So in this step, we figured out here that chloride is a spectator ion. It's present on both the reactant and product sides of the reaction. So lazy chemists can't stand writing things if we don't have to. We're going to pull the spectator ions out of this reaction. And when you pull the chlorides out, you end up with the magnesium metal plus 2H plus AQ, making H2 gas plus magnesium 2 plus aqueous. The chlorides are the spectator ions, and this, my friends, is what we call the net ionic reaction or net ionic equation. And this shows the action of the reaction, all right? The action here is magnesium metal reacting with acid to make hydrogen gas and magnesium. Chloride sitting around, not doing anything, not paying its rent, if you will. So what that means for a chemist, all right, is that if you really wanted to make the magnesium break up, you didn't have any HCl. Oh, the stockroom didn't order it. Oh, man. However, because chloride is a spectator, you could have used a different acid. So, for example, we could have used HNO3, nitric acid. We would have had nitrates as spectators, but we would have had the same net ionic equation. So net ionic reactions are cool for lots of reasons in chemistry, all right? Number one is they literally show the chemicals that are actually reacting. Spectators are pulled right out of the net ionic reaction. But on the other hand, the second cool thing is that let's say you wanted to do this reaction and we ran out of HCl, and this kind of stuff happens, all right? It's like, I didn't go to the store and buy potatoes or something. Well, instead of potatoes, maybe you can substitute sweet potatoes or, all right, that didn't work out so well. Anyway, in chemistry, you can substitute HCl then for HNO3, a different acid. You'll still have the H pluses reacting with magnesium to make hydrogen gas and magnesium, and you'll have a different spectator, but the overall reaction, the action of the reaction, same thing. Any questions on that? There's a handout online that you can get. It's called the Net Ionic Reactions Handout, and I wrote it specifically for this section, and it breaks down more equations, shows how to get the spectators out, how to find the net ionic reaction. Again, the punchline is when you go from the molecular equation, the balanced one, you don't want to break up solids, liquids, and gases. You're looking to break up the aqueous parts, definitely, but you don't want to break up the solids, liquids, and gases. Any questions on that? Cool. So we'll go through some examples, show how this stuff
A
works.
solution of lead nitrate is added to a solution of potassium chromate. A yellow precipitate of lead chromate forms, leaving potassium nitrate in solution. The potassium and nitrate ions do not take an active part of the reaction.
Cool. So this is a reaction where someone took potassium chromate, which is a solution that dissolves well in water, it's AQ, and they added it to lead 2 nitrate, and lead 2 nitrate also dissolves really well in water, it's aqueous. But when you mix them together, you get this really cool kind of yellow solid that appears. And when you see this, you might be thinking, I wonder what that yellow solid is. Well, aha! In this example, the lead chromate is what's forming. And when you look on that solubility guide, chromates, CrO4-2, almost always insoluble. And with lead, that's definitely the case. So in this case, it's the PbCrO4. Potassium nitrate also forms, but that thing is aqueous. So when you go through the steps, you'll see that the lead 2 plus and the chromate combine to make PbCrO4. The potassium and the nitrate here are both spectators. And what that means is if you didn't have potassium chromate, maybe you could add sodium chromate or something like that. The sodium could be the spectator instead of potassium, but you'd still have the same reaction. The yellow solid would still form. Again, solids, liquids, and gases will always be in the net ionic equation. It's the other parts, the aqueous parts, you can look at and stuff and see. So here's a reaction. Potassium hydroxide and iron 2 chloride are combining to make iron 2 hydroxide and potassium chloride. And it says what is or are the spectators in this reaction, all right? Now, we could go through and figure out the ions. So we'd look at the aqueous pieces, break them up into K plus, OH minus, iron 2 plus, chloride, etc. But remember, you never break up the solids, liquids, or gases. So that would be one way we could isolate them. But if you're going to have a spectator, it's going to be involved in aqueous pieces on both sides of the reaction. And so in this reaction, you can see how KCl is aqueous on the product side. This one's all solid. So iron here is not the same as iron there. You don't want to break up the solids. But K in an aqueous on this side is certainly the same as K on the aqueous on that side. So sometimes by looking at the products, you look at the aqueous part, which has both K and Cl, and on the reactant side, K is part of an AQ system, Cl is part of an AQ system. That means that both K plus and Cl minus are spectators. So again, I didn't break these up per se, I just looked for K and Cl, aqueous here, Cl aqueous, K aqueous. That's how I quickly found spectators. If you have a solid or liquid or gas, you don't break, those are not going to be spectators. So the iron is not a spectator, the hydroxide is not a spectator, because they ended up in a solid, liquid, or gas. Questions? All of the examples we have looked at so far are what they call exchange or double displacement reactions. And if you look at this one carefully, the K and the Fe like traded dancing partners, all right? So if you put the K with the Cl, that's where the KCl came from. And if you put the Fe with the OH, that's where the FeOH2 came from. So the next thing we're going to look at is how to predict what the products are so we can break them down into net ionic reactions and all that stuff. So an exchange reaction is kind of like a dance, all right? And imagine in a heterosexual world, you'd have a male dancing with a female and a male dancing with another female, and the males switch partners, or females, either way, all right? That's kind of the idea of an exchange reaction. So again, using very heterosexual, I apologize if that's offensive, but heterosexual ideas, A and B would be like males and X and Y would be like females. And they all trade partners. So A is now dancing with Y and B is now dancing with X. And again, because it's heterosexual, you have to have opposites, blah, blah, blah. That's kind of the idea of an exchange reaction, all right? The cations are trading places, dancing with a new anion, or the anions are trading places, dancing with a new cation. And this is real common in chemistry. So in this example here, the lead and the K are the positive parts, and they're trading dance partners. So lead starts dancing with I, and K starts dancing with NO. In the resulting products then, you have PbI2 and KNO3. Now, in an exchange or double displacement reaction, the charges on the metals and the nonmetals do not change. So in this PbNO3 the lead is a positive 2, and lead's going to be positive 2 on the product side. Likewise, K plus is positive here, and it's positive down here. So the reason it goes from PbNO3 to PbI2 is because lead is positive 2. You need 2 -1 nitrates and 2 -1 iodides to make it happy. On the other hand, over here, K is positive 1, so you just need 1 I minus to balance it out, but we need 2 to make the overall stoichiometry work. Same thing here, K plus NO3 minus 1 to 1, so we need 2 of them right there. This is a real common type of reaction in the kind of stuff we're looking at. And again, if you use the idea of like dancing people and they trade partners, all right, that's kind of what the double displacement reaction is all about. Any questions on that?
In combined solutions of lead nitrate and potassium iodide, a colorful material appears. This is actually a solid called lead-2 iodide.
So if you're a chemist doing this reaction for the first time, you would have a clear solution of lead-2 nitrate and a clear solution of Ki. And remember, solutions mean solute and solvent. PbNO3 would be the solute and water the solvent here. And on this solution, you'd have a K plus, I minus, Ki solute, and AQ means it's dissolved in water. And you mix them together, and all of a sudden you see a solid, all right? Well, something then is going to be written with an S on the product side. And you can use these exchange reactions to figure out what's happening. So the Pb and the K will trade places. Pb and I come together as PbI2. Likewise, K and NO3 come together to make KNO3. If you look back at that solubility guide, I minus is usually AQ unless it's with silver, lead, or mercury. Lead is one of the exceptions. This is how you can identify the solid. So in the lab this week, all right, there's several combinations of solutions, and you'll just mix some basically drops together. And if you see like a solid appear like this, you're going to go through and then identify what the solid is. And you can use this idea of exchange reactions, cations trading places with cations or anions with anions. And with the resulting compounds that form, you can look on the solubility table to see which one of them is going to be insoluble, i.e. which one you put a little S next to. As a chemist, this is cool because you mix chemicals together and you see something happen. What was that, Dr. Russell? Well, with my PhD, I'm using the exchange reaction more often than not to figure out what the products are and then what the possible identity of this cool yellow solid is that pops in. So, go chemistry. Anyway, questions on? A precipitation reaction is a type of exchange reaction, all right? And in this example right here, we mix some iron 3 nitrate with some sodium hydroxide. And the iron and the sodium trade partners, or the nitrate and the hydroxide, I don't care. You end up making sodium nitrate, which is Na plus and NO3 minus. But because iron is positive 3 here, it's going to be positive 3 down there. And hydroxide, OH, is OH minus. You're going to need 3 of those to make one of the irons, make a solid. You balance it out, you need to add 3s there. Now, in this example, nitrates and sodiums always mean AQ. So you don't even have to look those up on a table, you just know that they're AQs. Same thing over here. Here's sodium and nitrate together. This one is doomed to be AQ. However, hydroxide is usually insoluble unless it's with an alkali metal or sodium or ammonium. Alkali metals would be sodium, potassium, lithium. Then it's going to be solid. And iron is not an alkali metal or ammonium. This one is the insoluble compound that you see, or you will see. And when you break this down and you pull out the spectators, which here are sodiums and nitrates, you're going to see that the net ionic equation, or net ionic reaction, either way, iron plus 3 hydroxides makes FeOH3. You can identify the spectators from here. The sodium and the nitrate are aqueous on both sides. If you see a solid, liquid, or gas, it will be in the net ionic equation. You don't break those up.
In the test tube, we have an aqueous solution containing iron 3 ions. To this, we will add a solution of sodium hydroxide. A precipitation reaction occurs that produces iron hydroxide, an insoluble metal compound.
So at this point, the solid tells you that something has happened. You will write something with an S next to it. This is what they call a precipitation reaction. And precipitation reaction, precipitate is just a fancy word for a solid has formed, all right? We're going to start talking about why reactions happen. And the driving force is a way that we'll talk about it. So the reason precipitate reactions happen is that actually making a solid is a source of energy sometimes. And we'll see in the next chapter why that's the case. But anyway, making a solid a lot of times is enough for a reaction to happen, which is kind of exciting too. Any questions on that? Okay, this is a good place to stop. Let's take a 5-minute break. It's about 9:57, so 10:02. Stretch your legs.